now to the last talk on this part of the day. So Song-Ming, perfect.
Yes, can you see
yes,
okay.
perfect. So Song-Ming is going to tell us about now the Atlas results and prospects.
Okay,
Please,
thank you.
go ahead.
Yeah, thank you for inviting me to give this talk on the Atlas recent results and future prospect at this conference. So yeah, starting here in the brief introduction of the LHC. So I guess since all of you know about this, I'll just quickly skip through this. For the Atlas experiment, so it's one of the two general purpose experiment at the LHC. So here is a diagram of the detector. Starting from the most inner part of the detector, we have the inner tracker, which consists of the pixel detector, the semiconductor tracker, and also the transition radiation tracker. And surrounding the inner detector, we have the solenoid, which provide a magnetic field about 2 Tesla. And outside the solenoid, we have our liquid argon and tile calorimeter. And the most outer detector is our muon detector. So in run 2, the machine was colliding proton on proton at the center of mass of 13 TeV. And Atlas, we collected about 139 inverse bond of data that's good for physics. And the average number of interaction per crossing was about 34. And in our physics analysis, for most of the objects, reconstructed objects that we use, the uncertainty are at a level of about 1%, and the integrated luminosity uncertainty is about 1.7%. So in Atlas, we have a broad range of physics topic, and for today, unfortunately, I can only present short summary on a few of the recent results for a few topics, and also show some future prospect on some of them. So I apologize if some topics are highlighted more than the others. So starting with the Higgs boson measurement. So as mentioned just now, a Higgs-like boson was discovered at the LHC during round 1. And in round 2, we focus on measurement of its properties. So the major production channels, the GGF vector boson fusion, Higgs production in association with W or Z boson, and TDH, these production channels have been observed. And also the Higgs decaying into the H bosons, and also decaying to the 3rd generation fermions have also been observed at Atlas. So now we are looking for decays to the 2nd generation fermions and other rare decays. Plus, we are also improving the coupling measurement and also performing the fiducial and differential cross-section measurements, plus also searching for signs of new physics with the Higgs boson. So first, we have an update on the Higgs measurement going to WW and then decaying to E mu nu. So in this analysis, we measure the Higgs production in these 2 production channel, gluon-gluon fusion and vector boson fusion. For this analysis, the dominant background is coming from the continuum WW production and TD bar. And we make use of the difference in the azimuthal angle between the electron and muon. As for the signal, this angular difference is small due to the nature of the scalar particle. And for the gluon-gluon fusion, we use the transverse mass distribution as our discriminating variable. And for the vector boson fusion, we train a deep neural net to discriminate the signal from the background. And so from this, we measured the cross-section times branching ratio for the vector boson fusion channel and for the gluon-gluon fusion. So you can see here are the measured cross-section values compared to the standard model. So for the gluon-gluon fusion, our cross-section times branching ratio, we have obtained about 12% precision. And in the VBF channel, we have about 22% precision. Then we also have an update on the measurement of Higgs to ditau. In this channel, it has a relatively large branching fraction, so we can use the large statistics to study the Yukawa mechanism and also to measure some of the Higgs properties. So we made use of the full run-to data to measure this PP to Higgs to dital inclusively in the 4 dominant production modes, and also to measure this production in as a function of several key production properties. So the measurement of this dital is decay in these several different decay modes. And the main background is coming from Z to tau decay plus jet production. So the lab plot here shows the measured cross sections for these different production modes divided by the standard model prediction. So you can see the measurements are all consistent with the standard model, and the inclusive cross section that we measured is 2.9 picobarn compared to the standard model prediction. For this analysis, we also measure the cross-section times branching ratio in different bins of production and also in different kinematic region. So here we have the cross-section measurement for the TTH for PBF plus Dihix production. And in the case of the gluon-gluon fusion, we also measure the cross-section in different jet multiplicity bins and also in different bins of the transverse momentum of the Higgs boson. So you can see overall the measured cross-section are in pretty good agreement with the standard model prediction. We also have a new update on the search for the Higgs coupling to the charm quarks, which allow us to probe the Higgs coupling to the 2nd generation fermions. This is quite a difficult search at the Hadron Collider, partly due to the small branching fraction and also rather large background, plus it's also quite challenging to identify charm jets. So we developed a charm jet tagger to select the intermediate lifetime of the charm hadrons between the longer lifetime B and also the prom light quarks and gluons. So this using this charm jet tagger, we have an efficiency of about 27% in identified charm jets, and with about 8% efficiency in misidentifying a B jet as a charm, and 1.6% efficiency in misidentifying a light jet as a charm. So for this search of Higgs to CC, search is performed in the Higgs production in association with the W and the Z boson, and the Dicey jet mass distribution is used as a discriminating variable. So to validate our analysis strategy, we also measure this diboson production, where in one case, in the one of the diboson, we have the W decay to a charm and a light quark, and in the other diboson measurement, we have the Z decay to a pair of charm quarks. So on this right plot here, you can see the charm jet mass distribution after subtracting most of the background prediction, except the diboson background. So you can see a mass peak close to 80 GeV, which is coming from the W decay, and then maybe there's a small little peak here close to 90 GeV that could be coming from the Z decay. So our measured cross-section times branching ratio divided by the standard model are shown here. For the case of the diboson, you can see the ratio are close to 1. And in the case of the VH to CC search, we have a ratio of this measurement at around -9 with this rather large uncertainty. So with that, we set a limit on the cross-section of the VH to CC to be less than 26 times the standard model prediction, with an expected limit at 31 times the standard model. And we also set a limit on the Higgs to charm coupling modifier, this capacity to be less than 8.5. So here is a display of an event candidate of ZH to mu CC, where here the dimu mass, reconstructed dimu mass is at 92 GeV, and the reconstructed of the dichum jet mass is at 123 GeV. Okay, so Atlas has also recently combined all the major production and decay mode measurements, And using this combination, we obtain a global signal strength shown here with an uncertainty at around 6%. And here's a breakdown of the uncertainties. And from here, you can see that the signal theory uncertainty is the main dominant uncertainty source. And in this combination, we also obtain the production of the various production modes. And here we assume the standard model branching fraction. And in the production, we are now probing to about some % precision for the best channel, which is the gluon-gluon fusion. And in terms of the coupling measurement shown here, so you can see the measured coupling strength is in good agreement with the standard model prediction. And down here is the ratio with respect to the standard model. And you can see that the uncertainty of this coupling strength varies between around like 5% to 30%. Okay, so using this combination, we also extract the best fit values for the cross-section of different production process and also in different kinematic beams that you can see here. And plus, we also measure the ratio of the branching fraction. So overall, we see good compatibility with the standard model prediction. So now I come to the search of the Dihix production. So at Atlas, we search for the Dihix production in the gluon-gluon fusion and vector boson fusion production in several decay modes. So here is one of the latest updates in the Dihix search to BB gamma gamma. This is one of the most sensitive channel where it combines both the high branching fraction from Higgs to BB and also a clean low branching fraction of Higgs to diphoton. The main background from this analysis is coming from the diphoton plus jet continuum. And we search for the signal in the diphoton mass distribution, as you can see here, for example. So with no significant excess in our data, we set the limit on the Dihix production cross-section to be less than 4.1 times the standard model. And for the expected limit is at 5.5 times the standard model. So this result here is a factor of 5 times improvement over our previous measurement using 36 inverse Spandler bond. We also set a limit on the kappa lambda, which is the Higgs self-coupling modifier. So in the case of standard model, this kappa lambda will have a value of 1. So we set a limit on this kappa lambda to be in the range between minus 1.5 to 6.7. Then we also have another update of the Dihix search in the case of Dihix to BB tau tau. So in this channel, we select the events where one of the tau can decay leptonically and the other tau decay hadronically, or both taus decay hadronically. The main background coming from top production, WZ plus jet production, diboson, single Higgs, and also jet faking as tau. So in this analysis, we obtain an exclusion limit on the Dihix production cross-section to be less than 4.7 times the standard model, and with the expected limit at 3.9 times. Similarly, in this analysis, this result here is a factor of 4 improvement over our previous analysis. And this BB tau tau channel is the most sensitive single channel to the non-resonant Dihix search at Atlas. Okay, so we combined the results from both of the new Dihix search BB tau tau and BB gamma gamma, and from this combination we obtained the limit on the Dihix mass Dihix cross section to be less than 3.1 times the standard model, and the combined limit on the kappa lambda is between from minus 1.1 to 6.6. So at Atlas, we also make use of the Dihix search analysis to search for a scalar particle that decays to a pair of Higgs bosons. So combining all the results from these 3 Dihix search analysis, we set a limit on the cross-section of this scalar particle as a function of its mass. And you can see we set a limit in the range for the search range from 250 GeV to 3 TeV. Okay, so here is another display of an event candidate of the Dihix to BB tau tau, and the reconstructed dibjet mass is at 120 GeV, and the reconstructed of the di-tau mass is also at 120 GeV. Okay, now I switch to another topic, searching for heavy resonant W prime. So in this case, at Alice, we use the full run-to data to search for W prime decay to tau lepton. So in the sequential standard model, the W prime decay to lepton and neutrino is flavor symmetric. However, this coupling to tau could be enhanced for the non-universal gauge interaction model if the cotangent of this parameter theta nu greater than 1. So for this search, we select events with one hadronic tau candidate and large missing energy, and we use the transverse mass of the hadronic tau and missing ET as a discriminant to search for the signal. So shown here on the bottom left plot, you can see the transverse mass distribution, where you can see the data agrees well with the expected background. So with no sign of new physics, we set a limit on the W prime mass. So in the case of the sequential standard model, we excluded the mass below 5 TeV. And for the non-universal gauge interaction model, we exclude the mass up to 3.5 to 5 TeV, depending on the value of this theta nu parameter. Okay, so next report on the search for the lepton flavor violation. So as you know, so the lepton flavor is conserved in the standard model, but this conservation is not protected by any fundamental principle. And we have observed this violation in the neutrino oscillation. However, this violation is expected to be negligible for the charged lepton in standard model. So during run 2, there's about 8 billions of Z boson produced in Atlas. So we use these large statistics to search for lepton flavor violation in Z decays. So here are two analyses. One of them is we look at the Z decay to an electron or muon and a tau, where tau also decay leptonically. So in the final state signature, we have an electron, a muon, and a missing ET. And the background is mainly coming from Z to di-tau decay into electron and muon and the neutrinos. And we use the neural net classifiers to train to discriminate the signal from different backgrounds. So you can see here at the bottom, we have the neural net output distribution, and the data here agrees quite well with the predicted background, and you can see the dominant background is coming from Z to tau tau. For the other analysis is search for the Z decay to E mu, and so the final state is the same. We have E mu and the missing ET. And background is similar to the other analysis as I described earlier. So for this analysis, we search for peak around the Z mass in the E mu mass distribution. So you see here, the data also agrees well with the background prediction, and we do not see any peak. So using the results from both channels, we set a limit on the branching ratio of Higgs decay in this lepton flavor violation mode. So here is the results on the limit on the branching fraction from Atlas, and we compare that to the results from lab. So in the case of Z decay into E mu, the branching fraction limit from Atlas is about 5 times better than lab. And in the case of these other two channels here, the limit is about a factor of 2 better than lab. Okay, now I switch to search for dark matters. So at the LHC, the dark matter can be produced through the decay of a mediator to the dark sector, and we can indirectly detect it by measuring the standard model particles that recoils against it. So the signature will consist of a large missing energy plus X, where X can be a gluon, Z, W, or photon. So for the search of the dark matter, so the monojet analysis is a golden channel. And for this analysis, we select events with at least one jet with large PD greater than 150 GeV and large missing energy greater than 200 GeV. And in this analysis, we make use of the missing ET as a discriminant variable to search for the signal. As you can see here in the bottom, this is the distribution, where again, you see very nice agreement of the observed data with respect to the predicted background. So using this, we determine a model-independent limit on the visible cross-section range between 736 Vanderborn to 0.3 Vanderborn. And we also use this result to set a limit in the simplified model with axial vector mediator and a direct WIMP. So you can see the exclusion region shown here. X-axis, we have the mass of the mediator, and the y-axis is the mass of the WIMP particle. And here is the exclusion region. So from the monojet analysis, we can exclude the mediator mass up to 2.1 TeV for WIMP mass at 1 GeV. Okay, continue on the dark matter search in the Higgs to invisible decay. So in the standard model, the branching fraction of Higgs decay invisibly is about 0.1%. However, this branching fraction can be enhanced in some beyond standard model where Higgs couples to dark matter. So Atlas has recently updated the Higgs to invisible search using the full run 2 data and in several production mode of the Higgs boson. So you can see here the results of on the limit on the branching fraction of Higgs to invisible. And we combined the results from the VBA plus Higgs and TDH, and together with the round 1 search results, and obtained a branching fraction at 11%. So using this branching fraction limit, we then interpret it as a limit on the WIMP nucleon elastic scattering cross section in the Higgs portal model, but we assume the dark matter particles are either scalar or Mariana fermions. So you can see here the limit set on the cross section as a function of the WIMP particle mass. So this red and blue curve here are the results from Atlas. We can compare to the results from the direct search of the dark matter. Okay. Now I switch to supersymmetry. So in this analysis, I'm reporting the search is performed in the all hadronic final states. So for this analysis, we focus on the pair production of the heavy electroweak enons decaying into standard model bosons and also an LXP. So for this analysis, we exploit the large branching fraction of the hadronic decay of the bosons in order to increase the search sensitivity. So we use the large radius jet to capture the collimated energetic jets, and then we use the jet substructure to identify the hadronic decay of these bosons. So the final states will consist of large missing energy, 2 large radius jets, and no lepton. For the selected events, we group them in several orthogonal signal regions, as you can see here. So, and you can see the number of observed events in each of these signal regions compared to the expected predicted background. So we do not see any excess of data in this signal region. So these results are then used to set limits for several signal models. And one of them shown here is an exclusion limit on the Wino pair decay into a Bino LSP. So here is the plot. On the x-axis, you have the mass of the lightest chargino or the second lightest neutrino versus the mass of the lightest neutrino. So this all hadronic search analysis results are shown here. This is the exclusion region, where now it excludes the chargino mass of the second lightest neutrino mass up to around 1 TeV, which is now beyond the reach of the leptonic analysis, which is you can see here in the light blue region, which also made use of the full run-2 data. Okay, so here lastly, I report on the study of the B sub C decay to a J psi and D sub S or D sub S star. So this decay can occur through a B decay with charm as a spectator or through an annihilation diagram. So this decay was first observed by the LHCb and Atlas during round 1. And recently, Atlas has analyzed the full round 2 data in order to achieve more precise measurement of the branching fraction and also the measurement of the polarization. So for this measurement, we use this B sub C to J psi pi plus as a reference channel for the branching fraction ratio measurement. So the measurement of this ratio of the branching fraction is shown here. So we have the ratio of the branching fraction of B sub C to J psi ds over the branching fraction of the B sub C to J psi pi plus. And then we also have the ratio of the branching fraction of J psi of B sub C to J psi ds star to branching fraction of B of C to J psi pi plus. And then here is also the measurement of the fraction of the transverse polarization. So here are our new results, and you can also see this in this plot where we compare these new results with the earlier measurement from LHCb and Atlas. And you can see the results are consistent, but with better precision. Okay, so now I come to round 3 and high luminosity LHC. So round 3 will start next year with center of mass energy of the proton-proton collision at 13.6 TeV, and we expect we'll collect about 150 inverse femtobond during round 3, and this will increase the total data sample by a factor of 2. And the expected pileup during round 3 will be about 60. And for the high luminosity LHC, the expected delivered integrated luminosity will be about 15 to 20 times that of round 2, and the expected average pileup will be around 200. So currently Atlas is going through upgrades. So for the round 3 upgrade, we are finishing soon. And in terms of the trigger, so we expect we will have a higher purity in terms of the electron and photon triggers, and also with lower forward muon fake rates. And the calorimeter will have upgrade to the level 1 trigger electronics for the liquid argon calorimeter. And then for the muon, we will have a new sub-muon detector called the new small wheel. Then for the phase 2 upgrade, we expect we will have an increase in the trigger rate. For level 1, this will increase to 1 megahertz, and the high luminosity, so for the high level trigger, this will increase to 10 kilohertz. For the inner tracker, we will have a brand new detector with a repeated coverage up to 4. And then the readout electronics for the calorimeter and the muons will also be upgraded. Plus, we will also have a new high granularity timing detector located at the end cap of the Atlas detector. Okay, so I'll show here a couple of plots of the projected performance at the high luminosity LHC. So here is the case for the tagging of the B-jets, showing the B-jet tagging efficiency versus the light jet rejection. So for the run 2 performance, you can see the pink color line here, and the other curves here shows the projection for at the high luminosity LHC. So in the region of eta less than 2.5, for the high luminosity LHC, we will have an improvement by up to 50% compared to round 2, and we will also have a larger geometrical coverage to identify B-jets. And in the case of the diphoton measurement, for the mass resolution at the high luminosity LHC and with average pileup of 200, we'll have a comparable mass resolution compared to round 2 and for the optimistic scenario. So for the round 2, you can see is shown by these open diamond points. And for the high luminosity LHC in the optimistic scenario is shown by this open green circle here. Okay. Then I'll mention very briefly about the projection of some of the physics performance. So in the case of the Higgs measurement, for the measurement of the production, currently for at run 2, the gluon-gluon fusion is measured at 7% uncertainty, and the WH measurement is at around 20% uncertainty. However, at the high luminosity LHC, we could measure the GGF production at around 2.4% precision. And for the WH, this can be measured up to with about 8% precision. And for the coupling measurements, shown here is the projection for the high luminosity LHC, where you can see the uncertainty of the coupling measurements are around between 2 to 8%. So these are all below 10%, and you can compare to our current precision for run 2. And then here are recent projections for the VH to BB and VH to CC measurement. In the case of VH to BB, as shown here for the run 2 measurement of the signal strength, both the signal strength for WH and ZH, you can see that the uncertainty, the statistical uncertainty and systematic uncertainty are all around 19 to 20%. But at the high luminosity LHC, the total uncertainty will be below 10%, where the systematic uncertainty will be dominant, and the single largest source will be from the signal uncertainty. And in the case of VH to CC, as I mentioned just now, we have set an expected limit on the VH to CC to be less than 31 times the standard model using the full run 2 data. But at the high luminosity LHC, the projected limit on the VH to CC cross-section will be less than 6.4 times the standard model. Then for the projection of the Dihix search, so our projection shown here is based on the results from the run 2 analysis using 36 inverse Van der of data. So in this projection plot here, this is for the case of Dihix to BB tau tau. The y-axis shown here is the projected exclusion limit on the cross-section divided by the standard model as a function of the integrated luminosity. And you can see here are the several curves which correspond to different scenarios of the systematic uncertainties. And you can see this projection is quite sensitive to the systematic uncertainty scenarios. And then for the significance of the Dihix search, shown here in this table for different decay modes. So if you combine the significance from these 3 decay modes, you can obtain significance around 3 sigma. And if we combine with the CMS, then the projected significance will be around 4 standard deviation. But as I mentioned, reported just now, our recent full run 2 Dihix results have improved significantly over the previous 36 inverse Van der Waals results. So it is possible that at the end of the high luminosity LHC, we may reach the discovery level of the Dihix production. Okay, here are just a very quick report on the projection for the search of the dilepton and the L-nu resonant searches. In the dilepton case, currently right now with the run 2 data sample, so Atlas has set an exclusion on the Z prime in the sequential standard model at a mass of 5.1 TeV. So for the projection at the high luminosity LHC, this exclusion limit can increase by about 1.4 TeV. And in the case of the search of the W prime in the sequential standard model, for the run 2 analysis, currently the expected limit exclusion is at 5.8 TeV. And by high luminosity LHC, this exclusion can increase by about 2 TeV. And here a last projection for the high luminosity LHC in the dark matter searches. So this projection is using the monojet analysis with the run 2 data of 36 inverse Van der Waals. So on the left, you see a plot of the projection of the exclusion region in the mediator mass versus the dark matter mass. So this curve shows the projected exclusion. And this light dotted blue curve here shows the expected exclusion region currently using the full run-2 data from the monojet analysis. So you can see by the high luminosity LHC, the exclusion on the immediate mass can increase by several hundreds of GeV. Okay, so there are many more projection studies on the exotics and SUSY searches, which I cannot cover. So you can find these projection results at the in this link here. And now I come to my summary. So many new results from ATLAS have improved upon not just with more data, but also with improvement in the analysis methods. And a tremendous work has been performed by the collaboration to determine the physics potential at the high luminosity LHC. However, the reduction of the systematic uncertainties and improvement of the theoretical understanding plus innovation of advanced techniques will be important for the success of the high luminosity LHC program. And the run-3 data taking will start in a few months. So more exciting results will be coming soon. And in this link shown bottom here, you can find the link to all the recent results from ATLAS. Okay, that's all I have. Thank you. And sorry for taking so much time.
Thank you very much, really, for this very complete report on the most recent results from ATLAS. It's really amazing to see what, I mean, all these results with full run-2 data is really amazing. So we have time maybe for one question. I don't see any hand. And of course, as part of the ATLAS collaboration, it's hard for me to do some questions to you, but more than, of course, joining you in your last sentence, we have run-3 around the corner. We are all excited waiting for that. So yeah, stay tuned, because for sure we will have exciting results and hopefully some discovery, who knows. So I would like to thank you and all the speakers for this very, very nice session. And okay, we can close this part of the day, and then we see each other again in 2 hours.
Thank you.